Hello, today we'll talk about properties of transformations and especially linear transformations, since those are the ones we care most about. This is material from 1.9. So I think I'll start out with just a definition. Let me set the stage. Suppose T is a transformation, so just any old transformation without any assumptions. So, right, remember that this just means that this T is a rule that eats vectors in Rn and spits them out in Rm, okay? So the definition then is we say T is, there's gonna be two things. The first one is onto if each vector, let's say B, in Rm is the image of at least one vector, let's say x in Rn, okay? So this is maybe a concept you saw in pre-calculus in the setting of functions from the real line to the real line. I want to know if I take any vector that's in the codomain on the right-hand side, can I find a vector x that's on the domain that maps to it, right? That makes it in the image. And then a related concept is one-to-one. So we say T is one-to-one. If it's going to be a very similar definition, we just change one word. If each vector B in Rm is the image of at most one vector x in Rn. Okay, so this was at least, this is at most, okay? And so what this is saying is that if I take a vector that's, again, on the right-hand side in the codomain, then there's only one or zero vectors that map to it. There can never be more than one vector that gets sent to this vector B. And again, another concept you might have seen already in pre-calculus or other math classes. And I want to kind of give you a cartoon drawing of what these mean. In fact, I'll give you a picture of violations of these properties. So for the violation of onto-ness, let's say we're mapping from R2 to R3. So, here's my R3. And let's say that so the transformation T maps from one to the other. And let's say that I know that vectors in R2, here's my vectors in R2, all these guys. I know that they all get sent to a certain plane, let's say, in R3. So like, these four vectors get sent, I don't know, something like this. But no matter which vector you give me in R2, they always end up in this plane. Well, then what happens is I've got this vector, this vector B, this lonely vector out here. He's not in the club, right? He's not part of these vectors that get sent from the transformation because they're all in this plane and this vector is just sitting out there. So he's not a vector that comes from something. So this vector violates the condition. It's not coming from, it's not of the form T of x. So this is not onto, okay? For the one-to-one, let me give you a picture again. Maybe let's go from R2 to R3. And now let's say that I have a vector x and a vector y. And now what happens is when I apply the transformation, I know that they both get sent to, let's say, this vector here. So T of x is equal to this, and T of y is also that. So this is, T of x equals T of y. So what we're seeing here is that there's two vectors. If I chose this to be B, there would be two vectors that got sent to it, okay? That's a violation of this condition because I need at most one vector to be sent to that vector. This is a violation, so it's not one-to-one, okay? So that's the basic idea of these concepts. Now, what I want to do next is actually tie this to, connect this to the systems that we've been talking about. I mean, this is very abstract right now. This is just for general transformations. So let me recall, if T is a transformation from Rn to Rm, that is also a linear transformation, right? Then we saw last time, then it has what we call the standard matrix. Let's call it A. It's going to be an m by n matrix, right? M rows, n columns. where we know that when I apply the transformation to any vector, that's the same thing as just multiplying, right? Multiplying that matrix times the vector, and so this transformation is actually just represented by matrix multiplication. So in that case, we're going to have a kind of nice interpretation of what onto and one-to-one means. And maybe I'll just do this with an example so we have a concrete something to work with here. Suppose this is a linear transformation and it has matrix. It's from 4 to 3, so it should be a 3 by 4 matrix. Let's say it's 1, 0, 0, minus 4, 2, 0, 8, minus 1, 0, 1, 3, 5. Okay, so this is my matrix. It's 3 by 4. It eats vectors in R4, spits them out in R3. And the obvious questions I'm going to ask, is T onto? And let's say, is T one-to-one? Okay. So I think what I'll do is just kind of translate these notions, and we'll eventually see that it's going to look like something familiar, basically, right? So remember, onto means that each vector B is in the image of at least one vector x in Rn. So let me just maybe make a note here. So note that, well, remember, T of x is onto if and only if. What that means is that, in this case, A times x equals B has at least one solution for any B. Okay, so that's exactly what we're saying, is that I want, for any vector B, I want T of x to equal B, for at least one x. And that's the same as saying that AX equals B should have a solution for any B. And what you guys know is that, this is a matrix equation. So this is saying that A, the system, A augmented with B, has at least one solution for any B. And this is where we see that it connects to what we already know. This is the same thing as saying that A has a pivot in every row, right? So this is about rows. Onto-ness is about rows. Okay, great. So we now know that onto, if and only if, pivot in every row. What about one-to-one? You can probably guess what's going to happen, but let's write this out. Tx is, I should say T is onto, right? Not T of x. And here I mean T is one-to-one. If and only if, well, again, the translation is that AX equals B has at most one solution for any B. Okay, well, that's going to happen, right? Again, we go to the systems. That's going to happen if A augmented with B has at most one solution for any B. Now, what's that saying is at most one solution for any B means that, well, this is a system, so it either has 0, 1, or infinitely many solutions. I want to rule out the infinitely many, which means that I can have, an inconsistent system or a consistent system with one solution. What do I have to avoid? So I want to say that A has no free variables. All right, so remember, the free variables are what would make you have more than one solution. And as you guys know, this is saying that A has a pivot in every column. Okay, so one-to-oneness is about pivots in the columns. Okay, so let's actually answer our question, I guess. So is this guy onto? Well, yeah, look, we've got pivots are here, here, and here, right? So yes, pivot in every row, right? The pivots are, remember, onto-ness is about rows. One-to-one, if and only if you have a pivot in every column. Uh-oh, we're missing a pivot in column 3. So this is no, missing a pivot in, let's say, column, well, some column, it's actually column 3. Okay, so I want to actually, that's the idea, right? That's going to, again, this is how we translate this idea of onto-ness and one-to-oneness to just systems that we know and love. And I think let me just end with a kind of general fact that's going to connect this with other things we already know. So this is kind of a fact that brings in other facts, but just to kind of collect everything in one place. So this is kind of an important fact. Suppose T from Rn to Rm is a linear transformation with standard matrix M by N matrix, standard matrix A. Then maybe kind of two parts here. A, T is onto. So I just want to kind of translate what this means into different languages. So what we just saw is that T is onto if and only if the matrix A has a pivot in every row. And I want to now recall that last time what we saw is that having a pivot in every row can actually also be interpreted in terms of the vector equation by saying that the columns of a span are M. And let me just maybe remind you what that means is that every vector B in Rm can be written as a linear combination of those vectors, the columns of A. That's what it means to say that the columns of A span. Okay, and then the next part is kind of a characterization of one-to-oneness in terms of things we already know. T is one-to-one if and only if, well, again, the matrix A has a pivot in every column. Now, in terms of, again, I want to now interpret this in terms of the vector equation, where I look at the columns of A. Well, remember, to have no free variables, right, that's what this is saying, has an interpretation in terms of the vectors. And if you recall, what this was is that the columns of A form a linearly independent set. And maybe just to, for completion, let me just remind you what that means, that the system, the vector equation x1a1 plus, xnan equals 0 has only the trivial solution. That was the definition of being linearly independent. So I just want to, just so you have it in one place, that's the definition of what this last one means. So anyway, I'm actually going to pass out in class a sort of a worksheet or just a review sheet that has all this on there, but just so you have it in one page, more or less in one page. So we'll continue next time with these ideas.